Hi guys, so today we're going to talk about Chapter 8, Sequences, Series, and Probability. Today we are going to focus on sequences in Section 8.1. The word sequence is used in English. It's the same thing in math. It is a collection of numbers ordered with members. In math, we call them terms. You can think of a sequence as a function whose domain is the set of positive integers. Instead of function notation, where function notation we used f of x, for sequences we are going to be using a sub n. And that is talking about what term in the sequence you're talking about. So first term would be a sub 1, second term would be a sub 2, and so on. Nth term would be a sub n. The definition of a sequence. Notice A1, A2, A3, A4, all the way to AN, they are all called terms in the sequence. The domain of the function, if it is the set of only positive integers, we're only dealing with the first n positive integers. So once they put n, then that means that that sequence is finite. If not, it's an infinite sequence if it goes on for forever. So let's take a look at an example of a sequence. Part A there. We are going to talk about the first 4 terms of these sequences here. So part A sub n is equal to 3n minus 2. It's saying list the first 4 terms. So the first term, a sub 1, you're plugging in 1 for n and simplifying. So this would be 3 times 2. So a sub 1 would be 1. A sub 2, the second term, 6 minus 2, 4. The next 2 terms in the sequence are, the third term is 7 and the fourth term is 10. All right, part B. Go ahead and pause this and try this example. The first 4 numbers in this sequence in part B are 2, 4, 2, and 4. Let's take a look at these 2 infinite sequences. So we are trying to find the patterns. We're trying to find the expression to use for the nth term, a sub n. So let's take a look at example 3, part A, 1, 3, 5, and 7. In order to find the rule for the nth term, set up, write your n, and underneath of it, write your term. So term 1, so n is 1, is 1. Term 2 is 3. Term 3 is 5, and term 4 is 7. Take a look at how n relates to each of them and try to come up with a rule. If you notice, each of the terms based on n. So the first term, n is 1. The term is 1. When n is 2, the second term is 3. How does 3 relate to 2? As 1 relates to 1. So if you notice here, yes, these are all odd numbers here, but the rule, if we want n, we have to write this expression in terms of n. So maybe take a look at 3. How does 5 relate to 3 and 7 relate to 4? They all are 1 less than double n. So n can be written as 2n minus 1. If we plug any of those in, the third term, if we plug in 3, 2 times 3 minus 1 is 5, and so on. Take a minute and think about what the rule, what expression you could use for part B. Write out n and write out the term for each of the n's. And you are focusing on how the term relates to its position in the sequence. How does 10 relate to 3 in the same way 17 relates to 4? If you said n squared plus 1, you are correct. Each of these terms are 1 more than the square of n. A recursive sequence is one that relies on and is defined by using previous terms in your sequence. So let's take a look at this example here. They have to give you at least the first term. So in this case, a sub 1 is 3, and then a sub k is based on this a sub k minus 1. That means the previous term. So 2 times the previous term plus 1, where k is greater than or equal to 2. So your first term is going to be 3. Your second term is going to be 2 times the previous one, that a sub 2 minus 1 plus 1, that is 2 times a sub 1 plus 1. So 2 times this guy right here, 3 plus 1. So your next term is 7. Head and find the next 3 terms, because it asks for the first 5 terms. The next 3 numbers in your sequence are 15, 31, and 63. Hit pause and notice how each one is related to the previous one. I try to color code it here. So for example, this one, a sub 3, is 1 more than twice the previous number. So 2 times 7 plus 1. That is why the third term is 15. Our next definition in this section is a factorial. N with the exclamation point after it is, the way you say that is n factorial. It is the product of all of the positive integers multiplied together from 1 up through n. Notice the special case that 0 factorial equals 1. So for example, if I said 5 be the product 5 times 4 times 3 times 2 times 1 equals 120. Let's look at this example here. We are finding the first 5 terms of the sequence a sub n, where a sub n equals 2 to the n over n factorial, and it tells you to begin with n equals 0. A popular example of a recursive sequence is the Fibonacci sequence. Notice a sub 0 equals 1, a sub 1 equals 1, and a sub k is the sum of the previous 2 terms. So the work on the left here shows the beginning of the Fibonacci sequence. Take a moment and try the recursive sequence below. The next definition in our chapter is called factorial. The way you say this exclamation point here would be n factorial, which means the product of all of the positive whole numbers multiplied up through n. So 5 times 4 times 3 times 2 times 1, which equals 120. The special case 0 factorial always equals 1. So let's look at this sequence here that involves factorials. A sub n equals 2 to the n over n factorial. They tell you to start with n equals 0, so that would be the 0 term. A sub 0. The 0 term here would be 1, and a sub 1, the first term, would be 2. Find the next 3 terms of the sequence. The next 3 terms in the sequence are 2, 4/3, and 3/4. Look at simplifying factorial expressions here. If we have the expression 8 factorial divided by 2 factorial times 6 factorial, order of operations hold, you do factorials first. So 2 factorial times 6 factorial, write each of them out first and then multiply. Notice that 6 factorial is inside of 8 factorial, so all 1 through 6 cancel to make it easier to multiply what is left. and then you get 7 times 8 over 2, which simplifies to 28. Take a moment and try out this example problem. By definition, n factorial is 1 times 2 times all the way up through n minus 1 times n. N minus 1 factorial is all the positive whole numbers multiplied from 1 through n minus 1. Notice that n minus 1 factorial is inside of n factorial. So all of these terms will cancel with all of these. So you are left with n over 1, which is just n. The last piece that we are going to do today is the definition of summation. So that is the sigma symbol. So the sum of the first n terms of a sequence represented here. I is called the index, and n is the upper limit. And in this example here, 1 is the lower limit of summation. So let's take a moment here and look at the first example. We are taking the sum of 3i, where I is going from 1 to 5. It is the sum of the product 3 times I, and I is all the numbers from 1 to 5. All of the integers from 1 to 5. We are going to be adding all these up. Since 3 is a factor of all of the terms, I factored out a 3 and found it easier just to add 1, 2, 3, 4, and 5, which is 15, and 3 times 15 is 45. So that summation from 1 to 5 of 3i is 45. Next example, we're finding the sum of 1 plus k squared from, when k is 3 up through 6. Notice we are not starting with 1 anymore, we're starting with 3. So go ahead and find that sum. Notice each parenthesis here is a term in our summation. So this here, the summation notation, helps us to write out each term of our sequence before finding the sum. So each of these 4 are 4 terms of our sequence, 1 plus k squared, and the summation from 3 to 6 of our sequence is 90. Last example here. The summation of 1 over n factorial, where n is numbers from 0 to 8. For the sake of time, I have written these out for us here. So each of these are all the terms of the sequence. The sum here written out. All those factorials are written out for us. When we add those 9 terms up, we get this. Does that remind anybody of any value? If you said the irrational number e, you are correct. This summation is getting closer and closer. The more that we add to the summation here, the closer and closer we are getting to the approximation of the irrational number e. That's it for 8.1 part 1. Let me know if you have any questions. Thanks, guys.